The driving forces of thermodynamic favorability will determine whether a reaction will happen or not. Gibbs free energy is the maximum amount of energy released to do work, or it could be the energy required by a system for a reaction to happen. Gibbs free energy determines the spontaneity or thermodynamic favorability of a reaction, which refer to the same thing in Gibbs free energy. The first factor in determining favorability is enthalpy. Enthalpy is the heat energy lost or gained in a reaction. In an exothermic reaction, the change in enthalpy is negative, and it is written as a product. This is favorable because it releases energy into the surroundings. Endothermic reactions require energy. They're written with heat in the reactants and a delta H as positive. These are not favorable because energy is required from the surroundings to make the reaction happen. Very often the sign of the enthalpy change can determine the favorability, but this is not always the case, so we have to look at other variables. For example, ice melting into water. This is an endothermic reaction because it requires heat, but we know that this happens spontaneously because we see it happening. Ice melts at room temperature, but at 0 degrees Celsius, it remains a solid because there's not sufficient heat. So there's another factor in determining the favorability, which is the entropy. Entropy is the disorder of a reaction. It is determined by phase changes, the number of moles, or the volume of gas. In the universe, entropy is always favored. Disorder is always favored. If the delta S is positive, then the reaction is more disordering, but if the delta S is negative, then the reaction becomes more ordering. The picture on the right is an example of the entropy increasing. The gas particles move to fill the open space. Determining the sign for the delta S from a reaction is pretty easy. It is determined by phase changes in number of moles or the gas volume in the reaction. For the first example, it goes from a liquid to a gas, so it becomes more disordered and therefore delta S is positive. In the second example, the reactants are converted into 2 moles of products, which is more disordering because there's more moles of products, so S is positive again. And in the third example, the volume of the gas increases because 1 mole is being converted into 2 moles of gas. To find the driving forces of a reaction, we have to look at the 4 different cases. The first is when it is an exothermic reaction and the entropy is positive. Both of these conditions are favorable, so the reaction will always be spontaneous. We can say that the driving forces are both the enthalpy and the entropy. Looking at the equation for Gibbs free energy too, if the enthalpy is negative and the entropy is positive, the delta G will always be negative, which is favorable. And we know that the temperature is always going to be positive because it is in Kelvin. The second case we have to consider is an endothermic reaction that becomes more ordered. Neither is favorable, and if we look at the equation for Gibbs free energy, a positive delta H and a negative entropy will always result in a positive delta G, which is not favorable. The third case is an endothermic reaction that becomes more disordered. The enthalpy is not favorable, but the entropy is, so we have to look at the equation for Gibbs free energy. For the reaction to be favorable, the subtraction of temperature times delta S must be greater than the positive enthalpy. For Gibbs free energy to be negative, there must be high enough temperatures to make that term more negative than the enthalpy term, which is like the example of the ice from earlier. It is an endothermic reaction because it requires heat, but it is also more disordering. It will only happen if the temperatures are high enough. The final case is an exothermic reaction that becomes more ordered. The subtraction of a negative delta S term will result in a positive term. So if this term is small enough, then it will be favorable because the delta H is negative. So if the temperatures are low enough, this will be favorable. The driving force of the last 2 cases we looked at is whichever term, either enthalpy or entropy, is more favorable. For example, if we are given that the reaction as a whole is favorable, it is exothermic, and the entropy decreases, then we know that enthalpy is the driving force because it is the favorable term. It is what makes the reaction spontaneous. On the other hand, if the entropy is positive and the enthalpy are positive, and we know that it is spontaneous, we can say that the entropy is the driving force because it is what makes the delta G negative. So, when asked to determine the driving force of a reaction given that reaction and a term for the enthalpy, first determine the entropy of reaction by looking at the change in moles, a phase change, or a change in volume. Then select entropy or enthalpy based on which one is more favorable, or you can plug the signs into the delta G equation and figure out which makes the value more negative.